much for the introduction. Is the video and audio working well?
Yes, it is. Perfect, thank you.
Okay, so then, yeah, thanks a lot for having me, and I'll be talking a little bit about millimeter wave networking. It's research I started like 7-8 years ago when like a little of that was happening, and over the past few years the area has really exploded and it's become a very, very hot thing for 5G and 6G research and for local area networks. So I'll be talking a little bit about what I think are the interesting problems, what's the current status, and what are the important things that are not yet solved from my very personal perspective. So as a brief introduction, why millimeter wave? The main reason clearly is capacity. Only at millimeter wave frequencies do you have enough spectrum available to be able to have multi-gigabit data rates per user for many users. You can achieve this at lower frequency, right? So that's not the issue. But the problem really is at lower frequency, then you need very high order modulation schemes, you need very high order MIMO. Then if you have many users and very high order MIMO, you have channel hardening, it becomes much more difficult to actually achieve those MIMO gains. The overall multi-user MIMO complexity of the communication with the pre-coding and so on becomes very hard, right? So then if you really want to scale this up very quickly, you run into issues where it just becomes inefficient to do this for consumer devices. And another aspect that's really important, that's really helpful for millimeter wave, is that it uses directional antennas, and that makes spatial reuse very easy. In a sub-6 gigahertz setting, you can achieve something similar, right? With multi-user MIMO, you can have multiple users active at the same time, but that requires pre-coding and is complex. At millimeter wave frequencies, you achieve this in a much, much simpler way just by having directional antennas where energy is just emitted in one specific spatial direction where your communication partner is. And outside of that area, as is shown like in this little diagram at the bottom, you don't emit much. There's very low energy radiated there. And then you can pack many of those communication links next to each other without much interference. So those are the two big advantages. At the same time, there are a number of things that make this very hard. You have very high path loss, and most materials block the signal. Now, okay, that's fine. That means you have this primarily as a technology for smaller cells, but that's not a big issue per se. That most materials block the signal, that's a bigger issue, because, for example, if a person walks through a link, that will interrupt the link. And that, of course, is extremely undesirable if we're designing a communication system that's to be used for mobile communication. So communication is typically via line of sight, right? That means transmitter and receiver must be able to see each other. There is nothing in the middle that's blocking the link. Or, of course, signals are also reflected, right? You can bounce a signal off a wall if it's not line of sight. So to some degree, that works as well. And what this implies is that antennas have to be aligned. You need beam training, right? So basically, if we have this example at the bottom with a base station and a terminal communicating, they both need to know where the other one is so that the antenna beam can be aligned to point exactly in that direction. And if you move, you have to realign, otherwise you will lose the communication. So that as a quick recap of what's the technology, what are its characteristics. And now the current state is that we had first generation hardware for quite a while. That has been out for 5 years now, but it has not been widely adopted. So I'm pretty sure you won't have millimeter wave devices at home, even though those could have been, those were available already for a number of years. The standard never really was widely adopted just because the need wasn't there yet. You didn't have consumer demand yet for these very high data rates. The manufacturers didn't sell many of those devices, and for that reason, they never bothered to have updated versions of these devices, and so on. The use case just wasn't there yet. But it did one very important thing, which is it demonstrated feasibility. It demonstrated that these chips for millimeter wave communication with their very wide bandwidth and everything that implies can be manufactured at scale at a cost that makes them integratable in consumer devices with the hardware, with the hardware complexity and the energy consumption and device integration considerations, even for mobile devices. This has even been integrated on a mobile terminal, right? So it wasn't successful commercially, but manufacturers learned a lot about how to build those devices, and it's been shown that sort of once demand is there, it can actually be done. In terms of the problems of making the communication work, also there's been a lot of research on this beam training, right? How do you find out where the communication partner is? How do you adapt the beams and so on? And that works very well now for simple scenarios, right? So if the if the devices are static, of course, that's trivial. But even if the devices are not static and are moving, as long as there's no blockage, the current algorithms work reasonably well, right? To update the beams as the device moves along to make sure you don't lose the link. And in addition to first generation hardware, now much more recently, there is first deployment experience at scale. So one or 2 years ago, Verizon started its 5G millimeter wave network in the US and rolled this out in a few cities in the United States. And T-Mobile and AT&T were a bit more reluctant at the beginning, but then they followed suit, and now they're also sort of having their rollouts. But this is still very, very sparse and spotty, in the sense that in very big urban areas like Manhattan, you have a decent rollout and coverage at least some of the time, but most of the rest of the United States and the rest of the world, of course, is not covered. And that shows also a little bit the problems with this, right? So as we discussed before, if you don't have line of sight, you lose the link, which makes deployment extremely difficult, right? You have a street canyon, you put a base station there, but then you move behind a bus stop, and behind that bus stop, there is no connectivity, right? And that is something where for the end user, that's very hard to accept. And for the mobile operator, that's very hard to work around. You just can't put as many base stations as you would need to have ubiquitous coverage. There's also Facebook that's built a teragraph project using millimeter wave radios basically to build a very fast gigabit backhaul very cheaply, and they've gathered a lot of deployment experience with that. And they're using that for backhauling for like mobile networks in primarily developing countries, but also other use cases. So it's an area that's in its infancy, but the deployment is now starting, and we will see a next generation of millimeter wave devices in the coming years. Now, what's missing? As I've already mentioned, resilience is a big problem, and that is something physical that you can't work around, right? Like those waves simply do not penetrate an obstacle. You cannot improve your technology and suddenly they do. That's just like a limitation that you have. And what that means is whenever you have such a problem, right, you're taking your terminal and you're turning a corner or you're moving behind the bus stop and you lose your millimeter wave connection. Whenever that happens, you have to recover very, very quickly, seamlessly, so that the user doesn't even notice, right? And these kind of algorithms are not quite there yet. So what you can do is either very quickly hand over to a different base station that happens to be in line of sight with the terminal now, or use multiple technologies concurrently, right? So you can have multi-connectivity where, of course, your handset or your laptop or whatever will have sub-6 gigahertz technology as well, right? And then whenever you use your link, you have to very quickly fail over to the other interface that still has connectivity. And of course, then deal with a lot of other issues, because of course the sub-6 gigahertz link will have much lower rate and so on, right? So here, to make it work is quite doable. To make it work reliably most of the time so that the user is happy, that is a very hard challenge. Another issue is what I mentioned before in terms of the beam training. That works very well for simple scenarios, right? You have one access point, you have 5, 6 clients, and they move, and people walk around and they move, no problem at all. But now if we talk about mobile networks with hundreds of base stations, many different base stations to choose from, right? Because you need a dense deployment, again, because of this blockage issue and the range, right? So very often you will see many different base stations and many devices. Now, here the problem of beam training and network management becomes much harder. And this is something that I believe is still an unsolved problem for this area. You can also do a lot more than just communicate. So one of the big advantages here is that you have a very wideband system. And that gives you unprecedented insights into your wireless channel. You have an extremely fine time resolution because it is so wideband, which means like localization and tracking and sensing what goes on in the environment, where is a wall, where is a person walking, where is the next car, right? This is information that you now get for free from the communication, which you can also do this with sub-6 gigahertz, but there it was much harder, much coarser, and very often required sort of dedicated protocols, dedicated types of operating the network to make it work well for sensing tasks. And lastly, we need experience with more complex and compelling use cases. This was one of the reasons why first generation 802.11ad millimeter wave failed. There were just not the use cases and the user demand, right? And there are lots of ideas of what it could be: ubiquitous, augmented reality, virtual reality, manufacturing, autonomous cars, smart city, whatnot. But those use cases aren't quite there yet. And so that's certainly something very interesting. Like once you have them and once you need these data rates, that's also when you're going to learn a lot about how these systems really work in real deployments. So I'll primarily talk about the first two a little bit, simply because there's not much time in half an hour. So let me start. The challenges due to directional communication. So you need to have the directional antenna beams continuously aligned. Now, the more antennas you have on such a phased antenna array, right? So what a device has is like lots of little antenna elements. The more you have, the larger the antenna array, the finer the beams that you can generate, right? This is shown a little bit in this example with an access point with lots of sectors and a terminal, a handset with fewer sectors and less antennas, right? And so the more antennas you have, the more complex your antenna is, the more options, configuration options you have, and the harder the alignment problem. And then, of course, as mentioned before, it's short range and you have blockage. So you very often may have to do this alignment because you hand over to a different base station, and then you need to find out again what's the right direction in which to transmit. And now the big problem is in dense networks, this is a combinatorial problem, because you only know how good the channel is to a certain base station after you've done your beam training, right? After you've aligned your beams and the devices are properly configured. But then if you have a handover because your current base station is now blocked and you need a new base station, right? And you have 10 base stations to choose from. Well, you can't beam train with all 10 of them and then select the best one, because if every device did that, every time there is a handover, beam train with every possible base station just to figure out what's the optimum, your complexity becomes combinatorial, and like the network just doesn't scale anymore. You're using all the time just to beam train rather than to actually communicate in a more dynamic network with lots of mobility. So this is something there, like if you go to very high density networks, this will become a problem. Now, fortunately, there's something that makes this much easier to solve than it would be at lower frequencies. And that is that millimeter waves behave in a quasi-optical way, which means that things behave like you would expect them to behave geometrically. For example, let's take the little example that's shown at the bottom. You have a base station, you have a mobile terminal that wants to communicate with the base station. The fact that there is a wall in between tells you that you will not have a direct link, typically, right? So if you know that there's a wall, you know that you will not have a direct link. But if you know there is a reflecting wall at the bottom, And reflections, typically incoming angle equals outgoing angle. You know, if you know the geometry of the room, right? You know where the device is, you know where the base station is, you know where the wall is. You can just geometrically calculate at what angle you should radiate to bounce the signal off the wall and hit the base station. At lower frequencies, because it's a very rich multipath channel, you might partially penetrate the blockage, and it reflects the signal bounces from many different obstacles and walls and so on. This is an extremely hard problem. But in millimeter wave, the multipath is very sparse, right? So typically you have this one reflection, and you know where it is if you know your environment, and that allows you to configure your link. So the point here is this context information about what your environment looks like. That helps you a lot to solve this problem, because you don't need to try out all the possible combinations of base stations and directions. If you know what the scenario is, you already know like what is a good base station and at what angle should you transmit to reach it. So what we really want is a millimeter wave location system. Of course, any kind of location system would work, but ideally the communication systems should be self-contained, right? So ideally you would want to use the millimeter wave system to obtain this information about the environment and to then use that information to configure your network efficiently. So I'll talk about this next, how to design angle-based millimeter wave location systems. Why angle-based? Because you get angle information for free. Because if you do your beam training, that already gives you information about what angles to use. At lower frequencies, this is very simple. You have well-known algorithms like music and so on that do angle of arrival estimation and angle of departure estimation. They cannot directly be applied to millimeter wave because millimeter wave has multiple antennas, but it does not have MIMO. This is not a MIMO system where every antenna has an RF chain. It has a single RF chain only. So you only see the channel after the beam forming has already taken place. Now, you can still get angle of arrival and angle of departure information in many different ways. I'll just highlight a very simple one here. So what this shows is a few different beam patterns, right? So these configurations that are shown with very nice narrow sectors before, in reality, they look a bit more ugly, like we see on this with this blue outline, right? That's one sector. So now if you try multiple different sectors, what you will observe is a sequence of SNR values. And now if you know what your antenna patterns look like, the question you're asking is really, okay, given that I've observed this sequence of SNR values, which angle corresponds to this sequence, right? So we see low SNR, which corresponds, for example, to this angle we see here at like 27 degrees, but of course also to many others. But then many others will not also have a high SNR in the second step and an intermediate SNR in the third step, right? So then if you do a few of these tests, you can ask what's the most likely angle that generated this sequence of SNR patterns. That's one possible way of doing this. And that's sort of a compressive estimation approach to get angles from beam patterns. There are many different approaches. I'm not going to talk about them in more detail. The nice thing is now with this, you can actually do location estimation very easily if you know the geometry of a room, right? So for example, if the transmitter knows the whole geometry of the room, knows where the walls are, and the transmitter knows where it itself is located inside that room, then just by using angle of departure estimation and then following the line, it can pinpoint the receiver, right? The receiver is where the green line crosses the red line that is reflected at the known wall, and then the second order reflection from the yellow line and so on. And so that would be a very, very straightforward, very simple location system. Now, the problem with that is that in a real network, in a real deployment, you don't know where those walls are. You don't know where you are in the first place to then be able to locate the receiver. So what we're really interested in is a zero knowledge system that works on angles, or ideally works not on angles, absolute angles, but on angle differences, right? So the only thing you really know is that, well, I see something at angle 10 degrees and I see something else at angle 20 degrees and something else at angle 180 degrees in my own local coordinate system. Now, that doesn't tell you much, right? So the UE knows that sort of somewhere on this line in its own local coordinate system, access point 1 must be, because that's where it sees a signal from access point 1. And the same, of course, for access point 2 and 3 and 4. And now if the UE moves, of course, those angles change. Theoretically, you could just triangulate, but the problem is you don't know what the movement is either. Right, you cannot determine the black line that the UE moved to then say, okay, from this new position at this new angle, I intersect the lines and so on, because that's what you want to get in the first place. You want to build a location system that tells you that mobility. And the problem is exactly that, right? There are many different movements that, with the new angles that you observe at that new position, lead to different access point position estimates and are still consistent. So now how to build such a system? You can actually do it by looking at lots of measurements over time, right? So basically, if this is the first step, and then the angles change, but we don't know what the movement was, we have a lot of ambiguity because we cannot distinguish between those. But then if we take a first step, then if we take a third step, of course, the access points must still be in the same position. And the UE trajectory is typically not arbitrary, right? And so if we take many such steps and we want an estimate that tells that has the condition that the access point positions are always fixed, and the UE trajectory is not just completely random all over the place, but a sequence that makes sense over time, like a smooth trajectory, then we can actually postulate this as formulate this as a geometric problem and solve it. And this is a very hard problem to solve. It sort of requires higher order trigonometric polynomials and so on. But it is solvable, right? So the fascinating thing is you can build a location system only based on relative angle information, without any distance measurements, without any reference points. And okay, there are some tricks how to take into account that there are reflections and so on. The system works basically by first trying to determine likely positions of the access points or base stations. And then based on those, you try to pinpoint where the user is. And then after pinpointing where the user is, the user estimates give better estimates of where the access points are and vice versa, right? So you iterate over the system as you move more and more for longer and longer, you know more and more about the positions of the access point and the device itself. So you're making use of history to refine your system over time. And actually this allows you to build a system that's pretty accurate. So we've done some tests and you could achieve like down to decimeter level accuracy from relatively coarse angle measurements with such a system. And then if you have a trajectory over time, you can also estimate where reflections are coming from, and that tells you where the walls are, right? So that's a simple example here where the black crosses, this is where the system saw reflections and where it thinks that walls are. And of course, it might get that wrong at the beginning, but then as you see on the right-hand side, like the longer you run the system and the longer the trajectory, the correcter these estimates are. And then you actually have a system that can be used for localization and mapping. And then we want to use this location system for network control, right? So what I said before is we want to drive our handover and beam steering decisions directly from the estimated station location, right? If you know where the station is, then an access point just needs to beamform in that direction without having to do beam training. So the only overhead such a system has is the overhead, the linear overhead to run a location system that locates multiple devices. But it does not have the combinatorial overhead of every device beam training with every possible access point. And now, since you have estimation of a trajectory and you know where the walls are and so on, you can also do prediction and predict that soon there will be blockage, and for that reason you better hand over to a better base station. And so we've implemented such a system. This just very quickly to show what this looks like. We had complex trajectories. So on the bottom right you see a room with dividing walls in between. And we had trajectories that weave around through those walls, right? So you lose connectivity to one access point, then you see the next one, and then you lose connectivity with that one again, and so on. So that's like a nightmare scenario for millimeter wave. But if you know your trajectory and you can predict it a little bit into the future with dead reckoning, because it's a smooth trajectory typically, right? You can predict when you lose connectivity. And then on the right top graph, we use that to do a handover before the link breaks, right? This is this location-based scheme, and we see that there are no outages, whereas a standard scheme would experience outages. And so in terms of like the distribution of throughputs that you see, that makes a big difference in terms of like having resilient, reliable, good throughput. Now, I think I'm getting towards the end of the half hour, so I'll just very quickly go through the rest of it. There are many other important aspects, like multi-connectivity, for example. One issue is how do we do millimeter wave scalably, but the other one is if millimeter wave is not available anymore, how do we quickly hand over to sub-6 gigahertz or use both frequencies at the same time? And we've looked into this. It's not straightforward. For example, you can use multipath TCP, but then you get all sorts of interesting effects because you're combining sort of two very different interfaces with very different behavior. And so we worked on that a little bit to make sure that this works reliably, but you can actually get it to work, right? And that's a nice system. You get the sum rate of sub-6 and millimeter wave, which is very high whenever it's available, but it seamlessly just uses the lower rate sub-6 gigahertz link whenever the millimeter wave link breaks and is not available. And when it comes back, okay, then you have the high rate again. And there are many, many different topics that are also interesting that I'm not going to go into. For example, you can use it to build passive location systems that sense the environment, that see where there's movement in the environment, persons or a robot, and then pinpoints those objects very accurately. So that's very useful, for example, for environment sensing in industry scenarios. There are also very hard signal processing problems for millimeter wave, and some interesting aspects are to use machine learning for wireless physical layer design. At least to me, that sounds like a potentially very interesting topic. We're looking into this a little bit. And test beds are not easy at all. We've built a number of test beds, software-defined radio test beds, instrumented off-the-shelf devices for this purpose. All of this is public, so if you're interested, look at our website. And with that, let me come to the conclusion. So I think it's a very interesting, very promising area that's just sort of taking off. It's seen quite a bit of research, but now is the point where you actually see deployments. So now is the time when you get feedback from real-world deployments to see what the real problems are. We've also seen that conventional wireless network paradigms don't work very well, that those networks, millimeter wave networks, just behave very different from what you're used to. And what we've seen is that site information helps a lot. You can deal with these problems much, much better if you know something about your environment, if you can use anticipatory networking that predicts what's going to happen, and then you act before your link breaks. So with this, let me conclude. Thanks a lot for listening to the talk. And if there is time for questions, I'd be more than happy to take them. And otherwise, I'll be happy to receive your emails and answer them offline.
Thank you, Joerg, for giving us well, an interesting and hopeful perspective on how millimeter wave will help to make the puzzle for the 5G expectations. I see that there is a question in the chat from Peter. Peter, maybe you want to raise it yourself, or if you have a problem with the mic, I can do it, but you can also maybe raise it yourself.
Well, yes, I hope you can hear me. Well,
yes, we hear you.
I thought it had to do with the beam forming, the beam training, if you keep your mobile device stable, don't get a much higher quality.
I'm sorry, your link, like your audio is just breaking up, and now I can't hear you anymore.
So it says, because of beam training going on, does it mean that one's SNR will be much better if one tries to not tilt one's mobile device?
To not tilt the mobile device, you mean?
Or move it. So if you keep it stable, is it going to help to have a better SNR?
Yes, definitely. But also beam training works, right? It's not that it won't work if you move it around. You just need an algorithm that quickly counteracts that. And this goes back to then context information helps, right? For example, if you've got a mobile terminal with a gyro and a magnetometer and accelerometer, right? You can estimate how a user moved the terminal. And then you can counteract that. If the user moves the terminal 20 degrees to the right, then as a starting point, you can try to move the antenna beam 20 degrees to the left in the hope that this maintains a reasonably good link, right? And then beam training can also be done very quickly. So if it's not this very large network with many different base stations, if you're only trying to maintain one single link, then actually sort of even rotation that's typically fast is manageable, right? So yes, your SNR will degrade, but with current algorithms, you can still maintain a reasonably good link.